Hello and welcome to the YouTube channel D Creations Resources. We are discussing different aspects from science. Today we are going to discuss about interferometry and two specific interferometers, namely Michelson interferometer and Fabry-Perot interferometer. So first let us talk about what interference is. So when there is superposition of two or more waves, then the interference pattern is created. Now, depending on what the phase difference is between the waves, it can result into a constructive interference where the resultant amplitude is larger, or it can also result in a destructive interference where the resulting amplitude is smaller. So, if the waves are in phase, then you get constructive interference, while if the waves are out of phase, you get destructive interference. Now, this interference is manifested as alternating bright and dark fringes. Now, an interferometer is an instrument designed to exploit the interference of light and the fringe patterns that result from optical path difference. So, as I had mentioned, just like phase difference, path difference is a parameter which decides whether the interference is going to be constructive or destructive, etc. Now, in order to achieve interference between two coherent beams of light, an interferometer divides an initial beam into two or more parts that travel diverse optical paths and then they superpose to produce an interference pattern. For example, there could be wavefront division interferometers which sample portions of the same wavefront of a coherent beam of light. For example, in the case of Young's double slit. Or there are amplitude division interferometers like Michelson interferometer, where some type of beam splitter is used which divides the initial beam into two parts. Now, usually a semi-reflecting metallic film is used as a beam splitter, and here in Michelson interferometer you have a fixed mirror as well as a moving mirror, and the path difference between the two interfering beams can be varied by moving the mirror. Now, the other kind of interferometer, the FabryPerot interferometer, uses two parallel mirrors to create an optical cavity with multiple reflections occurring between the mirrors. Now, this FabryPerot interferometer, based on multiple reflections, is known to give sharper interference fringes and greater sensitivity to wavelength changes as compared to Michelson interferometer. So, if you want a better resolution, FabryPerot interferometer is a better choice. The fringes obtained in case of Fabry-Perot interferometer are called fringes of constant inclination or constant angle. Now, this system of two parallel mirrors is also called etalon. A spectroscopy technique like Fourier transform infrared spectroscopy makes use of Michelson interferometer, while an experiment like Zeeman effect makes use of Fabry-Perot interferometer. So, as you know, in Zeeman effect, there is splitting of energy levels due to magnetic field, and these split spectral lines are observed using the high resolution Fabry-Perot etalon. The interferometer produces a pattern with multiple fringes, where essentially each original spectral line is split into multiple lines due to the Zeeman effect. So, in a Fabry-Perot interferometer, the light incident on the first mirror is partially transmitted and partially reflected. The transmitted light continues through the cavity and is reflected by the second mirror. And this process will go on repeating, creating multiple beams of light that interfere with each other. So then from this, the interference pattern is observed at the output. And as you would expect, the distance between the mirrors is going to influence the interference pattern and the wavelengths that resonate within the cavity. Now, the fringes obtained in Fabry-Perot interferometer are circular because the interference pattern depends on the angle of incidence of the light entering the cavity. The phase difference between the reflected and transmitted beams depends on the angle at which the light is entering the cavity. As the angle of incidence will change, the path length traveled by the light through the cavity will also change. So this will lead to a different phase difference and hence the different interference pattern as well. Now, because the path difference and phase shift are directly related to the angle of incidence, rays entering at the same angle will constructively interfere at the same location on the screen. So this will result in circular fringes centered around the optical axis. And since these fringes correspond to all the rays that enter the interferometer at the same angle, the circular fringes are also referred to as fringes of equal inclination. To be more specific, here the condition for constructive interference, which is basically going to lead to bright fringes, is determined by the angle of incidence and the path difference between multiple reflections within the interferometer. So the fringes obtained in FabryPerot interferometer are going to be circular in nature. So when you do the Zeeman effect experiment, which incorporates a FabryPerot interferometer in it, you can see that the splitting that you observe on the screen is in terms of circular fringes, which are getting split in 3 or more depending on whether it's normal Zeeman effect or anomalous Zeeman effect, etc. Now the Michelson interferometer has a lot of significance in terms of history as well as in case of modern age. In history, it was used for Michelson-Morley experiment, where it was aimed for detecting the hypothetical ether, a medium which was thought to carry light waves. But the conclusion of the experiment was that speed of light is constant regardless of the Earth's motion, and hence it disproved the existence of ether. And in fact, it boosted Einstein's theory of relativity. And in today's age, modern age, in case of LIGO, the experiment based on gravitational waves, a Michelson interferometer is used. So Michelson interferometer has several applications, like for example, shift in the interference pattern can be used for determination of wavelength of light, or small distances can be measured, or changes in distances can be measured. Refractive index of a material can be measured. And as I mentioned earlier, measuring the speed of light or detecting gravitational waves are some of the historical uses of Michelson interferometer. Thank you.